Do parallel universes affect the decisions you make before you even make them? This idea has been explored in quantum mechanics, psychology, and even theories about consciousness. Some researchers suggest that every decision you make might not be a single linear moment, but a branching of possibilities. And here's a surprising fact to start with. Physicist Hugh Everett once proposed that every decision splits reality into multiple outcomes, all equally real. This is known as the many worlds interpretation. If that's true, then every choice you face might already exist in several different forms, and you might simply be the version who experiences one particular path. So tonight, we're not drifting away from the topic. We're going directly into it, slowly, curiously, like walking through a quiet library of unexplored ideas. Let's begin with the core of the mystery. When people hear the phrase parallel universes, they often imagine science fiction. But the idea began in physics, not fantasy. Here are two fascinating facts that form the foundation of the theory. Number one, quantum particles don't choose a single outcome until they're observed. Electrons can be in many places at once. Photons can behave like waves and particles simultaneously. This is called superposition. Some physicists believe this means reality itself holds many possibilities, side by side, until something selects one. Number two, the universe may be infinite, which means patterns must repeat. If space never ends, then matter can rearrange in infinite combinations. This implies there could be other regions of space where conditions are similar enough to create versions of Earth, and possibly versions of you. Now, how does this relate to your decisions? Imagine this idea. Your brain doesn't make decisions instantly. It evaluates multiple potential outcomes milliseconds before you consciously choose. That means your mind is naturally exploring parallel possibilities every moment. Some neuroscientists compare this to micro-parallel worlds inside the brain, simulations of different decisions before one becomes real. Let's connect that with another scientific puzzle. In the famous double-slit experiment, particles behave differently depending on whether they're being observed. Some physicists argue this suggests conscious observation selects a reality. So the question becomes, if reality branches into possibilities, and your brain already simulates multiple versions of events, could your mind and the universe be interacting in a deeper way than we understand? This is where the topic becomes even more intriguing. Not mystical, just open-ended, full of questions scientists still debate. Now, let's explore one of the most captivating ideas in modern science. If parallel universes exist, then there could be countless versions of you. Not clones, not copies, but natural outcomes of physics, each shaped by different decisions, environments, and circumstances. Here are three striking facts that support this concept. Number one, in Everett's many worlds theory, every decision you make creates a branch. One branch where you said yes, one where you said no, another where you hesitated, all equally real. Number two, if the universe is infinite, then statistically, someone with your exact DNA could appear more than once. This isn't speculation, it's mathematical probability. Number three, your brain already holds thousands of unrealized versions of you. Neuroscience shows that the brain constantly simulates alternative selves during planning and reflection. So the idea of another you isn't only theoretical, it also appears in psychology. Now here's a thought-provoking question that pulls the viewer deeper. If multiple versions of you exist, then is your decision truly singular? Or is it one path chosen out of many already existing routes? Some physicists believe that your consciousness moves along one branch of reality, while other versions of you continue along different ones. Not because you're split, but because the universe might naturally unfold in every possible direction. This leads to the central curiosity of our topic. If all versions of a decision already exist somewhere, what influences the version you experience? To understand whether parallel universes could influence your decisions, we first need to examine how a decision forms inside the human brain. Scientifically, decision-making can be divided into three major stages: preconscious processing, parallel evaluation of outcomes, and conscious selection. These steps unfold in milliseconds, but each plays a role in how you choose between possibilities. 1. Preconscious processing. Decisions begin before awareness. Studies by neuroscientist Benjamin Libet and later experiments by John Dylan Haynes show something remarkable. The brain shows signs of making a decision milliseconds before you become aware of it. This is called the readiness potential. The brain begins preparing several possible actions long before you consciously choose one. This suggests that your sense of choice is the final stage of a process that starts earlier and operates more automatically than you realize. 2. Parallel evaluation. The brain computes multiple futures. In neuroscience, decision-making involves parallel processing. Before choosing, your brain simulates different outcomes, assigns probabilities, evaluates risks, computes rewards, predicts future consequences. These simulations aren't linear. They occur simultaneously across different neural networks. This creates a structure similar to branching timelines inside the mind. It is not a multiverse, but it mirrors the same logic. Multiple versions of an event exist as potentials before one becomes the experienced outcome. 3. Conscious selection. The final path is chosen. After evaluating possibilities, the brain selects a single action. This becomes the reality you experience. But here is where the scientific curiosity emerges. If the universe itself contains multiple versions of every possible outcome, and your brain generates multiple internal outcomes before choosing, then both systems behave in parallel structures, one at the quantum level, one at the cognitive level. This raises a profound question. Is the brain simply mirroring the structure of the universe, or is it interacting with it? Quantum decision theories suggest that decisions might not be purely biological. Some physicists propose that consciousness could influence which branch of the universe we experience, based on selection of outcomes at the quantum level. This idea is explored by Max Tegmark, David Deutsch, and Henry Stapp. Though not proven, it provides a scientific lens to examine the central question: could your decisions be the result of quantum-level branching rather than ordinary biological choice? This is the primary question, and to approach it scientifically, we examine three major hypotheses. Hypothesis 1. Parallel universes exist, but they do not interact. This is the mainstream view of the many worlds interpretation, MWI. In this model, universes branch. Each branch evolves independently. There is no communication between them. If this hypothesis is true, then your decisions create new universes, but those universes do not influence you. They simply unfold in their own independent trajectories. Hypothesis 2. Quantum states influence decisions before they become conscious. This is proposed by physicist Henry Stapp. The theory says your brain contains quantum structures. These structures allow multiple potential decisions to coexist. Conscious choice collapses these potentials into a single experienced outcome. If correct, this means quantum events could bias your decisions before you become aware of them. Not because parallel universes talk to you, but because your brain might operate partly on quantum processes. Some evidence for quantum effects in biology include quantum tunneling in enzymes, quantum coherence in photosynthesis, and possible quantum behavior in microtubules. The last one is controversial, but the research continues. If quantum processes influence decision-making, then physics at the smallest scales may shape choices in ways we don't consciously control. Hypothesis 3. A weak form of parallel influence via probability structures. This is speculative but scientifically explored by researchers like David Deutsch. The idea is, if all possible decisions exist in separate universes, then your brain's decision-making might follow the probability distribution of outcomes across those universes. This does not mean communication. It means your decision might be statistically aligned with outcomes that are more probable across all branches. In simpler terms, if most versions of you choose something, the likelihood increases that you will choose it too. This is not proven and remains theoretical, but it is discussed in academic literature on quantum decision theory. The safest scientific conclusion is parallel universes could exist. They likely do not directly alter your decisions, but the mechanisms of decision-making resemble quantum branching, and quantum processes might influence choices indirectly. So the most accurate answer is, parallel universes may not influence your decisions, but both systems follow similar branching structures, suggesting a shared underlying pattern in how reality unfolds. While physics provides one side of the puzzle, psychology and cognitive science offer another. The idea of parallel universes aligns with how the human brain thinks, not literally, but structurally. Here's how. 1. The brain creates alternate selves automatically. Psychologists call this counterfactual thinking. Examples: what if I had chosen differently? What if I had taken that opportunity? What if I had said yes instead of no? These mental simulations serve a purpose. They help you learn. They help you predict. They help you avoid future mistakes. The brain constantly generates these alternate selves, just as physics proposes alternate realities. In decision theory, every choice is modeled as a branching tree with nodes, probabilities, and projected outcomes. This is identical to the branching structures in the multiverse model. The overlap is striking. Physics uses branching to describe reality. Psychology uses branching to describe cognition. You evaluate paths not taken, outcomes that didn't happen, versions of yourself that could exist. This is not imagination. It is part of human intelligence. Your brain is built to explore multiple potential timelines. In physics, uncertainty arises when multiple states exist at once. In the brain, uncertainty arises when multiple outcomes compete. Both systems resolve uncertainty by selecting one path. This is why the idea of parallel universes feels intuitive. It mirrors the structure of human thought. Does the brain detect parallel universes? There is no evidence that the brain perceives other universes. However, the brain predicts. It simulates. It constructs alternatives, which create an internal model of parallel possibilities. This makes the human mind aligned structurally with the concept of a multiverse. From a scientific perspective, one of the strongest theoretical foundations for parallel universes comes from quantum mechanics. The many worlds interpretation, introduced by physicist Hugh Everett, proposes that every quantum event splits into multiple outcomes, each outcome forming a separate, coexisting universe. Example: if a particle can spin up or down, quantum theory says it exists in both states simultaneously. According to MWI, instead of collapsing to one state, the universe divides. In one universe, the particle spins up. In another, it spins down. This implies an ever-branching structure of reality, where countless versions of events and even versions of you exist simultaneously. Another scientific pathway to parallel universes comes from cosmic inflation, the rapid expansion of space moments after the Big Bang. According to physicist Alan Guth, inflation may not stop everywhere at the same time. Instead, it creates multiple isolated regions of space-time, each forming its own bubble universe. These bubbles could have different physical laws, different fundamental constants, different types of matter and energy. In some models, these universes never interact because they are separated by expanding space, similar to soap bubbles drifting apart. This is known as the eternal inflation multiverse.
String theory, an attempt to unify all forces of nature, introduces another possible framework for parallel universes. According to the theory, the universe contains extraspatial dimensions curled up at microscopic scales. Different ways of shaping these extra dimensions lead to different physical conditions. This gives rise to what physicists call the string landscape, potentially containing 10 to the 100 to 10 to the 500 possible universes, each with its own particle types, forces, laws of physics. In this model, our universe is just one point in an enormous multidimensional landscape. 7. The holographic universe hypothesis. Another intriguing scientific idea suggests that our universe might behave like a cosmic hologram. According to this hypothesis, reality as we experience it in 3 dimensions could be encoded on a distant 2-dimensional boundary. If this is true, then other holographic surfaces could encode entirely different universes existing parallel to ours, but with different dimensional structures, different information patterns, and different physical laws. This concept comes from studies in quantum gravity and black hole thermodynamics, where information is stored on surfaces rather than volumes. In a holographic multiverse, our universe is just one projection among many. 8. Dark matter as a possible shadow universe. About 85% of the matter in the universe is invisible. We call it dark matter. It doesn't emit, absorb, or reflect light, but its gravitational pull shapes galaxies, clusters, and cosmic structures. Some scientists propose that dark matter might not be matter as we think of it, but instead a hidden sector of particles, interacting only faintly with our universe, possibly forming stars, planets, and structures we cannot perceive. This gives rise to the idea of a shadow universe, overlapping ours like 2 radio stations on different frequencies. We share the same space, but we experience only our own channel. 9. The mathematical universe theory. Proposed by physicist Max Tegmark, this theory suggests something bold. Every mathematically possible structure corresponds to a real universe. In this view, every possible set of physical laws, every possible equation, every possible geometry exists as its own reality. Our universe is simply one mathematical structure among infinitely many. This idea removes the distinction between math and existence, making the multiverse even larger and stranger than imagined. 10. Time as a dimension that creates parallel realities. In physics, time is treated as a dimension similar to space. If time can branch, loop, or stretch in different ways, then different timelines, different histories, different outcomes may all coexist simultaneously. Some models of quantum gravity suggest that time doesn't flow. Instead, all moments exist at once in a timeless structure called the block universe. If the block universe contains every possible timeline, then parallel universes are simply different paths through the same cosmic structure. 11. Quantum entanglement and the mirage of separation. One of the most astonishing discoveries in modern physics is quantum entanglement, a phenomenon Einstein called spooky action at a distance. 2 particles, once entangled, behave as a single system even if separated by light years. But here's the strange part. Experiments show that the correlation between entangled particles seems to transcend space itself. It does not weaken with distance. It does not fade with time. Some physicists have proposed that entanglement might be a bridge between parallel universes, a subtle hint that reality is connected in ways our senses cannot detect. Engaging thought. If particles can coordinate beyond space and time, could consciousness, in some unknown form, do the same? 12. Quantum fluctuations, the universe's endless lottery. At the smallest scales of existence, space isn't empty. It boils with activity, tiny fluctuations that appear and vanish in an instant. These vacuum fluctuations are not merely theoretical. They create measurable effects like the Casimir force. What's fascinating is that some models suggest these fluctuations might occasionally produce entire bubble universes, miniature versions of expanding space, completely different physical laws. This idea gives rise to the inflationary multiverse, where new universes are constantly budding off from the fabric of spacetime like cosmic soap bubbles. Hook. If universes can emerge non-stop from the vacuum, then your existence might be just one pattern generated from infinite possibilities, and countless other patterns may also contain you. 13. Symmetry breaking, the cosmic decision point. In the first fractions of a second after the Big Bang, the universe was a near-perfect ocean of energy. But as it cooled, its fundamental symmetries broke, like cracks forming in ice. Each crack represented a cosmic decision point. Depending on how the symmetry broke, the universe could adopt different forces, particles, constants, dimensions. So in one universe, gravity might be slightly stronger. In another, electrons might be lighter. In another, stars could form differently or not at all. This theory suggests that the universe we inhabit is simply one outcome of a deeper cosmic branching, where every possibility exists somewhere. Interesting twist. There might be universes where life is impossible, and others where it thrives in ways we cannot imagine. 14. Cosmic background radiation. Echoes from other realities. The cosmic microwave background, CMB, is the oldest light in the universe, a faint afterglow from 380,000 years after the Big Bang. When scientists examine it closely, they find cold spots, hot spots, anomalous patterns, unexpected alignments. One particularly unusual feature is the so-called cold spot, a region far colder than statistical models predict. Some cosmologists propose that this anomaly might be a scar, a subtle imprint from a collision between our universe and another bubble universe in the distant past. Imagine two expanding universes gently brushing against each other, leaving behind a faint ripple in the cosmic fabric.
In quantum mechanics, a particle doesn't choose a position until it is measured. It exists in a superposition, a blend of probabilities. Some researchers argue that the entire universe might exist this way. Instead of a particle being in many states, the universe itself could be in many configurations at once. In this view, there isn't just one cosmos, there are many, all coexisting as solutions to the same underlying wave equation. This concept is tied to the Hartle-Hawking wave function, which tries to describe the universe without requiring a beginning in time. If the universe is in superposition, then every version of its history and every version of you may be encoded simultaneously. The number of possible universes predicted by eternal inflation is so large that it dwarfs the number of atoms in our observable universe. In an infinite multiverse, every possible sequence of events, even the rarest one, not only happens, but happens endlessly. There could be universes almost identical to ours except for one tiny detail, and others where the laws of physics are so alien that we couldn't even imagine their landscapes. In string theory, the fundamental elements of reality are not point-like particles, but tiny vibrating strings. These strings can attach to higher dimensional surfaces called branes. Imagine our universe as a 3D brane floating inside a larger dimensional space, the bulk. Here's the striking part. Other 3D branes could float parallel to ours, separated by a microscopic distance in a direction we cannot perceive. To us, they would be invisible, but gravitational effects could sometimes leak between branes. This led scientists to wonder, could dark matter be matter on another brane? Could another brane contain life? Could cosmic events in a parallel brane affect ours through gravity? One theory even suggests that the Big Bang was caused by two branes colliding, releasing enormous energy. If branes drift and collide, then somewhere in higher dimensional space, another universe might be slowly drifting toward us at this moment. 17. Cosmic inflation and the multiverse factory. The early universe expanded at an unbelievable rate, faster than the light of speed, in a phase called inflation. But inflation theory predicts something unexpected. It shouldn't stop everywhere at once. Instead, some regions stop inflating, others continue, new universes form in the expanding regions. This process goes on indefinitely. This is called eternal inflation, and it means the multiverse could be an endlessly growing foam of universes. Each universe forms from a quantum fluctuation, gains its own physics, and evolves independently. The number of possible universes predicted by eternal inflation is so large that it dwarfs the number of atoms in our observable universe. In an infinite multiverse, every possible sequence of events, even the rarest one, not only happens, but happens endlessly. There could be universes almost identical to ours except for one tiny detail, and others where the laws of physics are so alien that we couldn't even imagine their landscapes. Time flows in one direction, from past to future. This is called the arrow of time, driven by increasing entropy. But here's the mystery. The laws of physics do not require time to move forward. They work the same backward. So why does time move in one direction for us? One explanation is that our universe began in a low entropy state, giving time a clear direction. But what about other universes? In multiverse models, each universe could have its own arrow of time. Some may move forward, some may move backward, some may have no meaningful time direction at all. Imagine a universe where events do not unfold sequentially. Time loops back on itself. Causality works differently. The past and future are indistinguishable. If time behaves differently in other universes, then the meaning of decision itself could change. Choices might not ripple forward, but in every direction at once. One of the most scientifically grounded ideas behind parallel universes comes from quantum decoherence. In quantum mechanics, systems exist in superposition. All possibilities coexist, but interference keeps these possibilities linked. When a system interacts with its environment, even through a single photon or vibration, the superposition decoheres. It doesn't collapse the wave function, it separates the outcomes so they can no longer interfere. Decoherence is essentially the mathematical boundary between parallel universes. Here's the deep part. As decoherence happens constantly, every microsecond, the universal wave function branches into different evolutions. Not magically, not philosophically, but mathematically through the Schrödinger equation itself. Parallel universes aren't added on top of physics. They emerge naturally from the equations we already use. The laws of physics in our universe seem suspiciously precise. If you change just one constant, even by a tiny fraction, stars might not form. Atoms might not bind. Chemistry might not exist. Life becomes impossible. This is known as the fine-tuning problem. Theories like string theory propose a solution. Instead of one universe with one set of laws, the fundamental equations may allow a vast landscape of 10 to the 500 possible universes. This number is not poetic. It's mathematically derived from different ways extra dimensions can curl and stabilize. Each configuration produces different particles, different forces, different vacuum energies, different physical realities. In this landscape, our universe is just one valley among an unimaginable number of possibilities. Interesting scientific angle. Some universes in the landscape would have no light. Some would collapse instantly. Some might have 4, 5, or more fundamental forces. Some might be lifeless but still exist as stable physical realities.
General relativity describes gravity and space-time. Quantum mechanics describes particles and forces, but unifying them, creating quantum gravity, remains unsolved. Still, some leading approaches imply a multiverse. Loop quantum gravity suggests space-time is made of quantized loops, atoms of space. These loops can form different topologies, like connected networks, disconnected regions, branching structures. Each topology could represent a separate universe emerging from the same fundamental quantum geometry. Causal set theory treats the universe as a series of discrete events linked in a causal chain. Different causal structures, different potential universes. Spin foams proposes that space-time fluctuates between different configurations, like a bubbling quantum foam, creating tiny branching universes at incredibly small scales. At the Planck level, space-time isn't smooth. It's a restless ocean in which universes can bud, merge, and vanish. In quantum field theory, the vacuum is not empty. It is the lowest energy state of a field. But here's the twist. There can be multiple vacuum states. Different vacuum states mean different particle masses, different interaction strengths, different forces, different physical laws. A shift from one vacuum state to another is called a vacuum phase transition, similar to water freezing or boiling, but on cosmic scales. False vacuum and true vacuum. Our universe may be in a false vacuum, a metastable state. A true vacuum could exist with lower energy, and in some models, a bubble of true vacuum could appear somewhere and expand at light speed, creating a new universe with different laws. Inside that bubble, time might flow differently. Space may curve differently. Particles may behave in unfamiliar ways. This isn't science fiction. It's a consequence of the Standard Model and its energy landscape. Vacuum energy determines the structure of reality. Shift the vacuum, and the universe becomes something entirely new. In quantum cosmology, scientists attempt to apply quantum mechanics not just to particles, but to the universe itself. One influential idea is the Wheeler-DeWitt equation, sometimes called the wave function of the universe. This equation removes the need for an external time. Instead, the universe exists as a vast quantum object. All possible states coexist within a single wave function. Time emerges only from relationships between states. In this perspective, parallel universes are not separate bubbles. They're patterns within the universal wave function, like multiple melodies woven into a single cosmic symphony. Striking thought. If the universe is fundamentally quantum, then the multiverse is simply its natural language. Black holes may be more than cosmic drains. They might be gateways to new universes. Certain models of general relativity suggest that a collapsing star forms a black hole. Inside the singularity, space-time doesn't end. Instead, it bounces due to quantum effects,
creating a new expanding region of space-time on the other side. In this model, every black hole births a universe. Our own universe may have originated in another universe's black hole. Physical constants could evolve through cosmic natural selection. This is called Smolin's cosmological natural selection. Just as life evolves through selection, universes may evolve too, favoring conditions that create long-lived black holes. Physics increasingly looks like information. Bits, interactions, codes. If the universe is fundamentally information, then it behaves like a computational system. In this view, physical laws equal algorithms. Particles equal data. Space equals the structure of information. Time equals the processing of states. This leads to the concept of a digital multiverse, where every possible computation corresponds to a universe with its own rules. This isn't metaphorical. Some versions of quantum gravity literally treat space-time as a quantum information network, woven from entanglement. The geometry of space might be the emergent product of quantum information itself. Entropy, the measure of disorder, drives the arrow of time forward. But entropy also sets the stage for a strange concept. Universes with different entropy conditions may naturally arise within a larger thermodynamic system. This implies high-entropy universes, low-entropy universes, universes with no directional time, universes where time branches or loops. The multiverse could be a thermodynamic landscape where different universes represent different ways information and disorder can organize themselves. Some cosmologists propose that universes spontaneously appear as low-entropy fluctuations in a larger eternal system. A growing movement in theoretical physics proposes something radical. Space-time may not be fundamental. It may emerge from deeper relationships, such as quantum entanglement, network geometry, tensor networks, information flows. In this framework, space-time is a structure that arises from underlying quantum connections. Different patterns of entanglement produce different geometries. Different geometries correspond to different universes. The multiverse becomes a catalog of all possible emergent geometries. Simulations using tensor networks can actually grow miniature universes from pure entanglement. The simulation idea is often presented casually, but serious versions exist in computational physics. If a civilization reached a high level of computation, it might simulate not just worlds, but entire universes governed by fundamental equations. Here's the scientific angle. Simulations can have different physics, different dimensionality, different particle rules, different computational substrates. If even one advanced civilization exists somewhere in the cosmic landscape, then the number of simulated universes could vastly outnumber physical ones. Hook. A simulated universe can simulate more universes, meaning simulations could stack like mirrors reflecting mirrors. Most people hear many worlds interpretation and think of branching timelines. But in actual physics, the idea is far deeper. The universal wave function never collapses. It evolves smoothly and deterministically. All outcomes exist simultaneously. Branching is not literal splitting. It's becoming non-interfering. This means parallel universes are not distant places. They are different mathematical solutions evolving alongside us in the same wave function. You don't jump to other universes. You are already a quantum distribution across them. Profound implication. Your consciousness is simply the version of you observing one path through an unimaginably bigger structure. We've traveled through quantum foundations, cosmological models, information theory, gravity, higher dimensions, vacuum energies, entropy landscapes, emergent spacetime, and the infinite branching of reality. And even after all of this, the truth is that the multiverse remains bigger than any single theory can capture. Every idea we explored, from brains to bubble universes, from quantum decoherence to emergent geometry, is a doorway into something deeper. Something still unfolding. Something we are just beginning to understand. And as you drift forward into your own quiet thoughts, you carry with you the awareness that reality is not a single thread, but a vast tapestry of possibilities, woven from the deepest codes of existence. Somewhere in the immense structure of the multiverse, other versions of your story continue their own journeys, curving through timelines, shaped by different choices, different histories, different branches of the universal wave function. And while this chapter of our exploration slows, the curiosity it opens remains endless, stretching forward like the fabric of space itself. In this universe, and all the others you'll never see, thank you for wandering through the science with me.